Alrighty, YouTube, welcome back. As you can see, I'm not in front of the C300. That's a good thing. It's not broke. Here in my little messy home office slash workshop, whatever. So it's going to be a little different video. I'm going to make a series of videos. I'm going to do something I've been wanting to do for a long time. I thought about it for a long time, and then I came across some YouTube videos with some other guy who's like really smart with this stuff. Who built an entire computer out of just transistors. You know, you always hear that computers are, basically just a bunch of transistors. It's all ones and zeros being saved and added and all that. And it really is, down to the most basic level. It's all transistors in there, ones and zeros. And, that's what a transistor is. We'll talk about. Here's a little transistor. This is an NPN transistor. It's a 2222, just a little general purpose transistor. And so we'll talk about transistors, and I'm going to make a series of these videos. I always thought it'd be cool just to like break it down, like to the very most basic level, how a computer works. And so now I can, because I can follow that guy's videos. And you can follow along with these ones too. And if you follow along, just like I'm going to be doing it step by step, you'll gain a much better understanding of how computers work as well. So, so stay tuned. This could be pretty cool. I have really no reason to do this. I just feel like doing it. So stay tuned. Okay. So I bought a bunch of stuff on Amazon, right? I bought some LEDs made in China, some switches, couple different values of resistors. We won't need too many of them, but they're like super cheap. It's like $2 or something for a pack of 100 or 1,000 or whatever it is. And I bought a bunch of breadboards, right? And check out this oscilloscope, if you know anything about oscilloscopes. Huh? We're going to check that out and see how that works. It was like, I don't know, $17 or something. An oscilloscope for $17. Look, it even came with a scope probe. Where is it? Right here. Came with a scope probe and everything for like $17, I think, on Amazon. So we'll see. I'm sure it's a piece of junk, but for what it's just good to have an oscilloscope so I can see what I'm doing here. Eventually, right now, we're going to see what I'm doing with LEDs. So this is a breadboard. This is what I'm going to build these circuits on, and we'll go over this circuit here in a minute. And you just need a power supply. This is just another cheap, made in China, DC power supply. What else do I need to talk about? So anyhow, these are 2222. Let me see what's the part number of these things. See how am I going to spill them all over the table. 2N2222. Very real common, little, basic NPN transistor, right? So you can look at this, maybe, if the camera will focus. It was focusing when I did it earlier. I tried filming this on the camera. Maybe I need to just sit it down. I tried filming this on the regular camera, the digital camera, and it wasn't focusing at all. I'm trying to get the lighting so it'll show the. There we go. I can almost see it. See, there's 2N2222. Okay, so this is a 2N2222. It's got 3 leads on it. They are called the collector, the emitter, and the base. And I always think of it like, in this case, when you look at the flat side, so I have the flat side of the transistor up. Can you see that? Well, I got to do some serious video editing here. The flat side's up, and so this is your collector. Your bottom one is your emitter, and the middle one is your base. And I think of it like the collector collects your signal coming in. Your emitter emits, really a lot of times it just goes to ground, but it's like emitting the current's going to flow this way. And the base is what allows, this is a little switch from your collector to emitter. It looks like an open switch right now. But if you apply a small voltage on the base, then it'll look like a short. This will close like a switch. From the collector to the emitter will act like a short if you put a little bit of voltage on the base. Okay, so it's an electronic switch, right? Electrical switch. You apply a small voltage, the switch closes. That's the idea with transistors. So let me get set up on the breadboard, and then we will come back to this 2222 transistor. Okay, so before we get started, we're going to talk about some of the components that we're going to use. First thing we have here is an LED. Everyone knows what an LED is, right? Little yellow LED. It's a light emitting diode. Here's two resistors, right? So these resistors, they resist the flow of current, and they have a color code band on them. You can look it up what it is, but I know brown is 1, black is 0. And the third band on these are 5%, I believe, resistors. They're either 5 or 10% resistors. So with 5 or 10% resistors, you have 3 bands. The first one is your first digit. Your second one is your second digit. And your third one is how many zeros come after that. So this is a 1, 0, and red is 2. So 2 zeros. 1 0 and 2 more zeros is a 1,000, right? So these are two, they call it 1K. These are two 1K resistors. So they're going to keep this little LED from just burning out. I'm going to put 5 volts on here. It's going to go through our transistor to ground. And if we just use the LED, maximum current would flow and this thing would just burn right out. So the resistor is going to slow that current down so that it doesn't burn out our LED or our transistor, too. Transistor would just fry open too. So we need a little bit of resistance there, slow things down. Okay, so we have an LED, some resistors, our transistor. This is just a little normally open push button switch. If I push it with my finger, it doesn't stay on the breadboard very well. If I push it, it closes. Let go, it opens. Here we have jumper wires that just help us get. Okay, so maybe I should talk about the breadboard first. So these rails are all tied together. This negative rail, all of these holes are tied together. This positive rail, these are all tied together. So I put my positive voltage here, so now all of these little holes along this rail have positive voltage on them. The negative ones, see I put my negative voltage down here, and so all of these holes have a negative voltage on them. These are all in rows. These are connected together, these are connected together, and so on, all the way across. And then these, same thing here. These are connected together, these are connected together. Not across here, though. Just these are connected, and then these are connected, but not with each other. This is the break in the middle. And then we have our transistor. So you can see here we have a 2222. See the 2222? It's a 2N2222 transistor. NPN, just a little common transistor that we use as a switch. It's an electrical switch. There's a collector, emitter, and a base. Those are the three leads on your NPN transistor: collector, emitter, base in the middle. It could be different on some transistors. Generally, these little ones, I think, are all about the same pinout for these little small signal transistors, I think they call them. So the collector is where my positive voltage is going to be. The emitter is where right now my negative voltage is going to be, or my ground. And then the middle is the base. The base is the part that turns this on. This is an electronic switch, basically. From my collector to emitter, it's open right now. It's normally open. If you check resistance across here, you'll get infinite resistance. It's open. No connection. When we apply a little bit of voltage to this base lead, that'll close these two. Current will be able to flow across these two leads. So it'll be like a closed switch. So a little bit of current, and we close this switch electronically. And so that's what we're going to do first, as you can see what I have here, I have an LED through a resistor to my collector. And then I have a resistor. You need one here too through the base to slow this current down, otherwise we'll fry this transistor. So I'm going to put 5 volts on this rail, and you can see, here's my little power supply. Maybe. There we go. See, we're at 5 volts. My lead's coming across to here, into here. So what we have is 5 volts to the switch. Right now the switch is open, so nothing's happening. But when I close the switch, we're going to apply a little bit of voltage to this base lead here, and it's going to close this transistor. And then that's going to cause this leg. Right now this leg is connected to ground, but this leg is just floating because it's not connected to ground. It's an open. So right now we have 5 volts through the LED, through the resistor to the collector, but there's no complete circuit because this is open. So the LED is not lit. When I push this button, it's going to close. Oh, it's falling out. When I push this button, it's going to cause current to flow here, a little bit of voltage on the base, which is going to close this circuit. And so then current can flow right through the transistor to ground. And we'll have a complete circuit. From positive, cross, back to the negative. We'll have a complete circuit, which means this side will be ground. This side is 5 volts. Current will flow, and this LED will turn on. So you can see, watch when I push the button, the LED turns on, right? So logic gates are going to act like they all have inputs and outputs, right? So this is going to be the input to this little logic gate. And right now the input is we call it 0. When it's off, an off is 0. 0 volts is off. 5 volts is on, or a 1 is on. So when I press this, that's my input is on. And now my output. The LED is my output, the button is my input. So when I make my input go to 1, my output goes to 1. So the output does exactly what the input's doing, right? 1, 1, 0, 0. Just follows what the input's doing. They call it a buffer. This is a little buffer, but all we're doing is using this transistor to make the output do the same thing as the input. This is called a logic table here. I probably should have drew input. I don't know, I can't do it looking through the camera. In, out. All right, so we got a buffer. If the input is 0, the output's going to be 0. See? 0, 0. If the input is 1, the output's going to be 1. We make the input 1, the output's 1. This is called a logic table. And it's for a buffer. It's super easy, right? Simple stuff. Okay, so that's the first logic gate. And here's the circuit. You can see the circuit here pretty clearly because, you know, it's not much there. This jumper wire has no purpose here. It's just in the way. So, pretty easy to see. And when you look over here, this is our voltage supply. Here's our two 1K resistors, our LED, our push button switch, and here's the transistor. And this is how you draw a transistor on a circuit diagram. An NPN, if this arrow is pointing out, it's an NPN. If this arrow is pointing the other way, go back to my screwdriver. If this arrow is pointing the other way, then it's a PNP transistor. And then everything just kind of works backwards. I don't know, I never really used a PNP transistor, so that's just my understanding of it. PNP kind of works backwards. Anyhow, here's an NPN. So you can see our voltage is applied here. When we close the switch, the base is going to allow current to flow across here, which will take our voltage across our LED through our resistor. It will cross the transistor, go to ground, and that'll complete our circuit, and the light will turn on. The LED will turn on. That's a buffer. Okay, pretty good. You can see the scribble scratch behind here where the first attempt at drawing a buffer. Anyhow, okay, so that's a buffer. So next thing we're going to do, we're going to build on each one of these things. We're going to build on. So after a buffer, we're going to build something called an inverter, which does the opposite. When our input is 1, our output's going to be 0. And when our input's 0, our output's going to be 1. So it's going to be just the opposite of the buffer, right? So now we can make a change. You know, when we push something, the output's going to be something different. So let me build that circuit, and then we'll check back. Okay, so you can see what I changed here. Before, with our buffer, we had the LED going from the power through the LED, through the resistor, through the transistor. So now we made a little change. Now we have power going directly through the resistor to the transistor, to the collector, and then it's going to go through to the emitter. And then we have the LED on the collector as well, going to ground. So what happens is I'm not doing anything, and the circuit is being made, right? The base is open, this is not conducting, but the LED is on, and the reason is we have our 5 volts here going through the resistor, through the, these are all connected together, right? So it's going through the resistor, through the LED to ground, automatically, directly to ground. So without doing anything, our LED is going to light, which is our output. So our output will be on with doing nothing. So what's going to happen is when I push the button, I close this, that's going to allow current to flow through this transistor to ground, which means right now one side of this has a voltage on it from here through this resistor has a voltage. Whenever I close this circuit, this is ground, this is ground. Whenever these two are shorted together, that makes this ground. So one side of the LED will be grounded and the other side will be grounded. So there's 0 voltage potential there. So the LED will turn off. So this is what's going to happen. Ready? So I have a 0 at my input and a 1 at my output. Now when I apply a 1 to my input, I get a 0 at my output. It's the opposite, right? A 0, 1. So let's look at our truth table of our inverter. What did I draw it right here? And on this one, I didn't write an in or an out either. In. And of course, my pen stops working now. Out. So my in is, actually I drew this backwards. I should have put the 0 on top and the 1 on the bottom. So when my in is a 1, my out is a 0. When my in is a 0, my out is a 1. See? We've inverted it. We've inverted our signal. Input is a 1. Input is a 1. Output is a 0. We've inverted it. Input is a 0. Output is a 1. That's why it's called an inverter. We inverted the signal. And you can see the new schematic right here, how I wired it. Voltage, same thing here. Our switch is going to close. Apply a little bit of voltage to the base, which is going to close this circuit. We got our 5 volts here through the resistor, and then it goes from here through the LED to ground. So by doing nothing, leaving this open, we have voltage flowing straight through the LED, so we get a light. But when we close this, that shorts these two together. That closes this switch, which causes this to be ground, because it's right here. It causes this point to be ground, which means the LED is ground on both sides, so it's not going to light. Makes sense? Pretty cool, right? Inverter. Very basic. We're going to slowly build on these and get just slightly more complex each time. Okay, so the next circuit we're going to build is an AND gate. This is the circuit diagram. This is our logic table, and this is the schematic diagram. This is what it would look like on a schematic. And this is what our logic is, because it's called an AND gate. So look, now we have 2 inputs and 1 output. So if our first input is 0, our second input is 0, our output's going to be 0. If our first input is 0, second input is 1, our output's still going to be 0. And if our first input is 1, our second input is 0, our output is still going to be 0. But if our first input is 1 and our second input is 1, our output will be 1. So now we probably should learn a little bit about binary numbers, right? So in a decimal system, we have 10 characters, 0 through 9. That's how our decimal number system works. Some people don't even really think about it like that, but that's how it works. So in a binary number system, we only have 2 characters. We have a 0 and a 1. And so you start with 0, and then if you want to count up in binary, you go to 1. Well, then after you get to 1, what do you do? Because you don't have a 2, so we have to add another line. Add a 1 here and a 0, that's 2. That's a binary 2. Not looking at this is our output. Just looking at these 2 columns. We start with 0, 1. Now to get to 2, we have to add a 1 here. It's our carryover, right? Like in decimal. So if we have a 1 here and a 0 here, that's 2. Now to get to 3, we can add a 1 in this column, and we have a 2 plus 1 is 3. And then if we want to continue to get to 4, you can see how you would have to add a 1 in the third column, and 0, 0 would be 4, and so on and so forth. And 1, 0, 1 would be 5, 1, 1, 0 would be 6, 1, 1, 1 would be 7. And it just builds like that. And so the numbers get really long. In a decimal system, you have 10 characters. So to get to 100 only takes, actually to get to 1,000, really, if you're counting 0, only takes 3 characters. You can get to 1,000. Well, you saw here with 3 characters, I only got to, what was it, 3, 4, 5, 6, 7. I only got to 7 with 3 characters instead of 999 or 1,000 if you're counting 0, right? So, but the good thing about that is computers are really good at long numbers, counting and keeping track of really long numbers. What they're not good at is different characters. There's either electricity on this transistor or there's not. And so if there's electricity there, it's a 1. If there's not, it's a 0. So computers are plugged into a receptacle in the wall. It's electricity. There's no magic input to a computer that has pictures and does math and all that stuff. There's nothing magic. It's just a 1 or a 0. Either the transistors are turned on or off. And we're slowly going to build on this to see how just with 2 transistors, looking at our schematic, with 2 transistors, we can show numbers up to number 7 already, right? Well, no, because I didn't do the 4th column. We can show numbers up to 3, right? A 1 and a 1 in binary is a 3. So with just 2 transistors, we can show a 0, 1, 2, and 3. 0, 1, 2, and 3, right? So, okay, so maybe that's enough of that for now, right? So let's just show the circuit in action. And so here's our 2 inputs and our output. And so we are going to, I got my 2 resistors here for my 2 inputs. And this is the resistor for the LED for the output. And here's my 2 transistors. And so look, I have my collector. My base is going to this switch here. My emitter is tied to the collector here. This base is going to the other switch. And this emitter is going to ground. And so when we look at this circuit, you can clearly see if I don't close either one of these switches, power is not going to get past here. So this LED is not going to turn on. But if I close this switch, power will get through this, current, I should be saying current. Current will get through this transistor. If I close this switch, current will get through this transistor, but then it's going to stop at this one because this one's not closed. But if I close, and let's say I open this one and I close this one, well, this one's shorted, but current's never going to get past this one even to get to this one. So, but if I close both of them, now current can flow straight through to the ground and complete the circuit, and the light turns on. And that's how we get an AND gate. And so the next video, we're going to build on this with NAND gates and exclusive gates to show how we can do some pretty interesting things with just 1s and 0s. So that's our AND gate. Let's do it on here. It's kind of crappy using these little dip switches is all I got right now for switches. It'd be easier if I just had like two nice push button switches. But anyhow, so let's show. If I turn the first one on, nothing. Okay, let me turn it off. Turn the second one on. Still nothing, right? But if we turn both of them on, still nothing. Oh, hang on. Let's start over with that. It's really hard to do when I'm looking through the lens of the camera. Okay, so, okay, let's start over. Okay, nothing. Take our first input. Jeez, now I'm knocking out resistors. Turn it on. Nothing happens. We still have a 0. A 1, 0, 0. Turn our second input. Again. 0, 1 is still a 0, just like our truth table, right? 0, 1 is still 0. But if we turn both of them on, we get a 1. 1 plus 1 is 1. So you can see how the truth table works, right? Pretty cool, right? That's an AND gate. This input and this input will give you an output. One or the other will not. All right? So if you can imagine what our next logic gate will be, it's going to be called an OR gate. So let me get that put together and we'll check back. Okay, now look what we have. We have an OR gate. Okay, that's what an OR gate looks like on a schematic diagram. Here's our truth table. Now look what happens. We still have two inputs. And by the way, they make 3 input, 4 inputs. They make OR gates and AND gates with many inputs. But, you know, we're just learning the beginnings here. So we're going to start with 2 input. ANDs and ORs. All of the gates we're going to make today are going to be 2 input and 1 output. So anyhow, with our 2 input OR gate, we have a 0 on input 1, a 0 on input 2. That gives us a 0 on the output. Same as the AND gate, right? Here's where it's going to differ. If we have a 0 on input 1, but we have a 1 on input 2, we have an output of 1. Also, if we have an input on 1 and a 0 on input 2, we still have an output of 1. Pay no attention to my blob here. Started with a really ugly 1 and got even uglier as I went. So also, if input 1 and input 2 are 1, if they're both on, we get the output on, a 1. When I say on and 1, that means the same thing. 2 inputs are on, our output is on. But if one input is on or the other input is on, we get our output on. If neither, then our output is off. Right? Makes sense? So let's look at the schematic. How do we do that with 2 transistors? Well, look, it's very easy. Here's our power source. We have 2 switches, 1 and 2. We have our same deal with the LED, resistor, LED through the first transistor. Resistor, LED, but look, this symbol here, my drawing is very ugly. My handwriting is terrible. This symbol here means there's no connection here. This wire is just jumping over that one and coming. No connection here. So look, we have power coming through here, and it's going to both transistors, and then their emitters are going through ground. And then so we still have the same 2 inputs, right? Same 2 inputs, but instead of them being in series, now they're in parallel. This is a parallel circuit. Parallel means the current can flow in more than one direction. It can go this way, or it can go this way. In series, it's only one path for current to flow. So now that we put these 2 transistors in series, what happens is if we close this switch, but we leave this one open, that turns this base on, which turns this transistor on and shorts this. So current will flow through our resistor, through our LED, through this transistor, and the light will turn on. The LED will turn on because we have a path for current, right? But if we open this one, if they're both open, then they're both not connected to ground, so the LED cannot turn on. There's no path for it to get back around to complete the circuit. But you just saw if we close one, there is a path and it will turn on. If we open this one and close this one, that turns this transistor on, which means there's a path and the light will turn on, right? This one or this one. But if we turn them both on, now there's a path here and a path here. Either way, it's still electrically, this point is the same as this point. So the LED will turn on. Current will flow probably half of it this way and half of it this way. And the light will turn on. So that's why we get our logic gate. Both off, no output. One on, get an output. The other one on, we get an output. Both of them on, we get an output. So that's why it's called an OR gate. It's this input or this one will give us an output. This input or this one gives us an output. And both of them gives you an output. So that's an OR gate. So there's two very useful little logic gates. And so the next thing we want to do is add one of our previous logic gates to this. Oh wait, let's see. Here's my little circuit. We gotta check it out. This is boring stuff. This is where it's cool. Okay, so look, this is what I did. I got the same two resistors to the same two switches, same resistor here to the same LED. This same transistor collector is tied to the LEDs going to the collector here. All I did was take this transistor out and I spun it around. See how it's backwards? So that this is its collector. It's also connected here. Both collectors are connected here, which is what you can see. Both collectors are connected to the LED, right? And so both emitters go to ground. And so that's what I did. This emitter goes to ground. This emitter goes to ground. And then both bases, this base goes to this switch. This base goes to this switch. Both bases to our switch. So we built that circuit, right? And now let's see it in action. So if we turn on the first switch, look at that. Got light. We turn it off, turn on the second switch. We got light. See, current's flowing through this way on the second switch. And if we turn both switches on, we still have light. Because now it could go either direction to make the circuit for the light. So that is our OR gate. One or the other. One or the other or both gives us an output. That's our OR gate. Okay, let me figure out what we're going to do next. I think we're going to add an inverter to this. We're going to add an inverter to this AND gate, so that we're going to make the output opposite. We're going to go 1, 1, 1, 0. We're just going to make it the opposite because it can be useful. An OR gate, and so it's called a NOR gate. No, this is a NOR gate. Whenever we put an inverter on here, hang on, scratch all that. That was too confusing. So all we're going to do is take our AND gate and our OR gate, and we're going to put an inverter on the outside, on the output of it, to invert whatever this output is, make it the opposite, right? Because we already made an inverter on our previous page. Let me flip over to it. See, we already made an inverter right here. Whatever's on the input, it makes it the opposite, right? So we're going to add this circuit to our AND, and we're going to add it to our OR gate to invert their outputs. It's going to be a NAND and a NOR gate. Kind of silly, right? They made it NAND and NOR, but hey, it makes sense, right? Easy to remember. Okay, so let me get those set up and then we'll check back. Okay, we made a NAND gate. Here's the schematic symbol. See, it has this extra little thing. It's called a NOT. It makes whatever would have been here not what it is. Here's our logic truth table. You can see it's opposite. Here's our AND gate. AND gate. We have 0, 0, 0, 1, right? Only a 1 when both. Our NOT AND gate, or our NAND gate, is, disregard the half zero there. My hand worked faster than my brain. 1, 1, 1, 0. It's the opposite of our AND gate, right? 0, 0, 0, 1, 1, 1, 1, 0. See? 2 zeros gives us a 1. A 0 and a 1 gives us a 1. A 1 and a 0 gives us a 1. And a 1 and a 1 gives us a 0. It's the exact opposite of an AND gate. And here's how we built it. So the AND gate is built like this, right? With 2 transistors. And we saw how current can only flow through to turn this on if both of these switches are closed. This one and this one, right? Well, in this case, all we did, we have the same circuit pretty much. These 2 transistors are only going to close if this one and this one are closed, right? These are only going to turn on. But instead of our LED being up here, waiting for these to close to turn on, now it's over here, where it can turn on before we do anything. It's on. And it will only turn off if this one and this one, or if these 2 inputs are on, both of these transistors turn on, current flows through them, makes this point to become ground, right? So that'll turn off the LED. Ground on either side, it's not going to light up, right? So that gives us our truth table, right? Because with both of them open, the LED can be turned on. Oops, I forgot something on my LED. Forgot the little light symbols, lightning bolt symbols, whatever. So you can see how it's the opposite of an AND gate. Opposite. But all we did was move the LED from here to here. Does it make sense? Both of them open, no current flows. Power goes this way, turns the light on. This one closed, still no current flows because this one isn't on. LED stays on. Close this one, open this one, still no current can flow if this one's open. LED stays on. Close both of them. These 2 transistors turn on, which essentially makes this. It's one shorted wire, essentially. And which makes this ground. Both sides of the LED are the same voltage potential. Nothing happens. Doesn't turn on. That's our truth table. All right, so let's see it in action. Look, see, all I did was I moved the, let me get better lighting. All I did was I moved the LED from up here. I just stretched this resistor all the way down to the collector here. And then I put this LED on the other side of the collector to ground, just like we showed here. Just like we show it here. From the collector to ground, here it is. From the collector to ground, the LED. And so let's see if it works. Okay, already we have the LEDs turned on. Hang on, let me put it with the truth table here. Light this up a little. So the switches are off, the LED is on. See? I turn the first one on, the LED is still on, our output is still on. I turn the second one on, LED is still on. I turn them both on, and the LED goes off. So our truth table works. So we have made a NAND gate. Pretty cool, right? We made the output be opposite of what it would have been with an AND gate. And so in OR gates, basically we're going to do the same thing with an OR gate, right? We're going to move our LED over and let me build it. Let me draw it and build it. We're going to make a NOR gate, okay? Okay, so we've built our NOR gate. Remember our OR gate over here? We got an output if one or the other or both inputs were turned on. If both or one or the other gave us an output. If neither, we got none. So our NOR gate, all we did, we moved our LED from here to here. Essentially, could be tied in anywhere along here. It's all the same electrical point. So we tied it in right here. So you can see with both switches off, whoops, I Didn't finish my circuit. Do this little thing here. My pen would work. Okay, finished my circuit. So you can see with both switches off, current can flow through this resistor, through the LED, makes a closed circuit. So the LED is going to turn on. But if we close this switch, it's going to short this, right? This is going to be closed. And then this becomes ground. This is ground. The LED will turn off. If we open it and we close this switch, just like the OR gate, this is going to close, and that's going to make this ground. And this is ground. The LED will turn off. And if we close both of them, then, of course, this is going to be ground up here. The LED is not going to turn on. The LED will only be on when they're both open, which is the opposite of the OR gate, right? The LED was on only unless if they were both open is the only time it was on. Well, now the only time it's on is when they're both open. Did I say on over here? The only time it's off is when these are both off. Anytime any of them are on, it's going to be on. Over here, the only time it's on is when these are both off. It's the opposite. 1, 0, 0, 0, 0, 1, 1, 1. Right? Here's the schematic symbol. It's got the little not symbol in front of it because we made it opposite. And so let's see this circuit in action. Okay, you can already see our output is on. Both inputs are off. Our output is on. It's jiving so far. So we turn the first one on, it goes off. Turn the second one on, our output goes off. We turn both on, our output stays off. Just like the truth table says. So we made basically an inverted OR gate. It's called a NOR. Okay? So with these logic gates, you can do all kinds of cool stuff. So we got one more logic gate to talk about, and then we'll end this video till next time. And it's called an exclusive OR gate. So let me get that one built, and we'll check back. Okay, so here's our next gate. It's called an XOR gate, or exclusive OR gate. This is what the schematic symbol looks like with my crappy handwriting. Here's our logic gate. So if we look at an OR gate right here, you can see we have 0, 0, 0. If they're both off, we get an off. In every other case, it's on. If one's on, it's on. If the other's on, it's on. If they're both on, it's on. Well, an exclusive OR gate is kind of like an OR gate because if they're both off, it's off. If one's on, it's on. If the other's on, it's on. But if they're both on, it's off. So 0, 1, 1, 0 is our output. So it's just a little bit different, and it's a useful gate. So let's go through the schematic here. So here's our output up here. I did a crappy job of drawing this. But let's follow our output. So I had to just draw it this way, A and B. Here's A and B. So we can just assume this is tied to here, and the B input here is tied to here. So let's go through it. If they're all off, these are off, that means this has some voltage here. So this is on, right? Because you have a path for current to flow through these two resistors that turns this on, right? Which makes this ground, which makes these ground. But these are both off, right? These are both off. So even though this is ground, there's no path. So the LED is off. So if they're both off, the LED is off. If we turn one of them on, here, this is basically an AND gate here, right? These two need both to be on. So if we turn one of them on, that turns this on, but this is still off. So this part of the circuit is still off. This part of the circuit is still on. So these are still grounded, we've turned one on. We've turned A on, right? So now there's a path for current to flow because this is on here, right? So if we turn one on, if we turn A on, we get an LED. We get a 1 on our output. And you can see, we turn one on, we get a 1 on an output. And obviously, if we do the same thing with B, it's going to be the same thing. This part of the circuit is going to stay off, which leaves this part of the circuit on, which gives us the path to here, and B is on, so that gives us the path for current to flow through the LED to turn it on, back to ground, to make the circuit complete, right? So if this one is on and this one is off, we still get an on at the output, right? But if we turn them both on, that makes this part of the circuit active, right? So this is basically shorted to ground here, which makes this circuit, which makes this transistor turn off because you have ground here, ground here. This transistor is not going to be turned on. So there is no path with both, even though both of these are on, the current can flow through the LED through both of these, but it can't get through here. So that's going to turn the LED off. And so that's how we get our exclusive OR gate. Both on, the LED turns off. So we got a 0, 1, 1, 0. Does that make sense, everybody? Pretty cool, right? Something different. And then in the next video, we'll use these gates. And so you can just, I can show you, there's one more gate that you could make. It's an exclusive NOR gate, which would just move this LED out here like we did with the other, with the NOR gate, right? We move the LED out here so that it has this plus. So it's opposite of the exclusive OR gate. You'd get a 1, 0, 0, 1. And it would have the little bubble here. So those are our logic gates for this video. Pretty cool. Oh wait, let's watch it. Let's watch it in action. We should get a 0, 1, 1, 0. Okay, so we got our 5 volts. Circuit's running. No output. Both inputs are off. So let's turn one input on. Look, we have an output. Okay. Let's turn the other. Okay, so my microphone died. So here I am. I'm just going to do a voiceover. So yeah, here I am. I followed the logic gate, right? I turned one input on, got an output, turned the other, got an output. Both of them got no output, right? So followed the logic gate. Pretty cool, right? Yeah. So anyhow, here was my just closing for this. Anyhow, I hope you guys enjoyed it. I hope you guys got something out of it, learned a little something with me. We're learning about transistors and logic gates. Pretty cool, huh? We're doing some neat things. So the next video, I'm going to make, I'm going to combine some of these logic gates together and see what kind of neat things we can do combining logic gates together, how we can possibly store ones and zeros for later. Anyhow, so I hope everyone enjoyed it. And if you liked it, subscribe. You can click the like button and that helps the algorithm, whatever, So anyhow, I'll see you guys on the next one. Have a good day.